Lesson 2.7, Dilations. Alright, so our goal today is to understand our fourth and final transformation, which is how to create dilation transformations. In other words, how to shrink or enlarge objects. Okay, so what we're basically trying to achieve here, and the reason why it's been separated from the other transformations, is that this is the only transformation where the shape we end up with, let's say this was the original and it was blown up to make this shape here, is that it's not congruent. All the other transformations we did, reflections, rotations, translations, you always ended up with the same exact congruent shape. But here, we don't end up with a congruent shape, we end up with a similar shape. And so this is why we separated out the last transformation, dilations, until now, because now that we've talked about similar shapes, we have a little bit better understanding. Now, first thing you'll want to know is, well, how can you tell whether two shapes are actually similar, or they just look similar? Okay, well, one way to tell is that, of course, the angles should be the same. The corresponding angle should be the exact same angle. And then, just like with scale factors and what we've talked about with similar shapes, that these shapes should all have the same ratio. Now, another way to do that visually is to actually find what's called the point of dilation. In other words, there should be a point, well, let me just show it to you. If I take this corner here and I draw a line and match it up to the corresponding corner, but then I extend it to a certain amount, and then I do that with the other corners. Let's take this top vertex here, the top vertex here, but then continue it, and making sure I'm lining up right here, like so. And then I do it with the third and final vertex to here, that they should all match up in the same location, which is right here. This is what we call the center of dilation. All right, because it's the one place, I like to think of it as a flashlight. If this flashlight were beaming outward, it would hit this object, and then this is the shadow that it's casting. And so this is a way to physically tell whether or not two shapes are actual dilations of each other by matching up the corresponding vertices and to find that one spot where all three lines meet up. All right. Now we're going to also look at dilations mathematically. So to dilate a figure with respect to the origin, meaning that the origin is always going to play the role of that flashlight I was talking about. So if this was an example we actually did, this would be the origin, 0, 0. What you do is you multiply the coordinates of each vertex by the scale factor of k. In other words, what we're going to do in the next couple examples is we're going to take a shape that's already on graph paper. So each of the vertices is on some coordinate. To get the dilated version of that, you just take each of your coordinates and multiply it by some scale factor k. So if it was 3 times as big, k would be 3. If it was half as big, k would be 1/2. And that leads us down to this small note here, but it's an important one, is when that scale factor is bigger than 1, it's going to be an enlargement. So if it's 1.227, 200, you know it's going to be enlargement because the scale factor is larger than 1. But then anytime that scale factor is somewhere between 0 and 1, some fraction, then it's going to be a reduction. 1/2, 1/4, 2/3. It's going to make the object smaller. All right, so let's take a look at a few examples. Let's take a look at this first example of dilation with respect to the origin. Now, of course, the origin is where the x and y axis meet, 0, 0. And so what we're going to do is we're going to start off with our pre-image, our original shape. So we've got the vertices of some triangle ABC, and here's the coordinates. So let's quickly graph these. So across 1 up to 3, there's A. Across to 2 up to 3, there's B. And across to 2 up to 1, there's C. So I join those together. There's my triangle. And so what we're going to do is we're going to do a dilation by a scale factor of 2. Now, first off, what that tells me is that since this is larger than 1, it means we're doing an enlargement. In other words, scale factor of 2 means we're going to make this twice as big with respect to the origin. Now again, with respect to the origin just means that instead of going from the origin to here, we're going to go out twice as far. We're going to do that for this one, and we're going to do that for C as well. So imagine it's almost like a flashlight shining on some triangle, and then behind it, somewhere twice as far away, that shadow is going to hit the wall. Now, to find this mathematically, though, of course, what we're going to do is, like was said earlier in the presentation, is we're going to take the scale factor of 2, and we're just going to multiply everything by it. So in other words, I'm going to do times 2. And so A prime is going to end up at the location 2, 6. I just doubled both my coordinates. Same thing here for B. I'm going to multiply everything by 2, get B prime, which will be 4, 6. And multiply this one by 2, and I'll get C prime at 4, 2. So 2, 6 is right here. That's A prime. B prime would be at 4, 6, which would be right here. And C prime would be at 4, 2. All right, so if I've done this correctly, what I should get is a version of this triangle twice as large. And I can see again those projection lines. If I match up A and A prime, they lead back to the origin. If I match up B and B prime, they lead back to the origin. And if I match up C and C prime, they lead back to the origin. All right, so that's how we incorporate the coordinate system with our understanding of dilation. We no longer need the rubber band activity we were doing earlier, which is not all that accurate. This is a more mathematical way to calculate these things out. All right, let's try another one. Now this one's a little different. We've got a rectangle, W, X, Y, Z, and these are its vertices, which we're going to graph. And as you graph these, -4, -6, you'll notice that what makes this one different is that these shapes are a rectangle is actually over the origin itself. You'll see what I mean as I finish up here. 4, 8. That's Y. 4, -6. That's Z. So our rectangle is right here. All right. So now what we're supposed to do is dilate it by a scale factor of 1/4 with respect to the origin. All right, which is a little different with the point of dilation in the shape itself. Over here, it was over to the left and below our shapes. But here, it's dead center. But that doesn't matter. What that means is that, first off, that since this scale factor is between 1 and 0, dilation, we mean we're going to actually shrink it instead of enlarge it. And what we're going to do is it's basically going to shrink towards the origin. So in other words, Y here is going to shrink some distance this direction. W is going to shrink towards the origin this direction. Same thing with X, and same thing with Z. Okay? And so that's how we can still dilate with respect to the origin. These things are all just getting either closer or further away, depending on whether it's a reduction or an enlargement. Now again though, the easier way to do this is just do it mathematically. What we're going to do is we're going to find W prime by multiplying everything here by 1/4. So W prime would be 1/4 of -4, which is -1, and then -6 times 1/4, or another way to think about it, -6 divided by 4 is -1.5. X prime, same thing. We're going to multiply by 1/4. So -4 times 1/4 is -1. 8 times 1/4 would be 2. And we just keep going. Multiply by 1/4 for Y prime. That'd be 1 and 2. And multiply by 1/4 for 4 and -6. Z prime would be 1 and -1.5. All right, so now if I graph these, -1, -1.5 would be right there. That's W prime. -1, +2 would be right there. That's X prime. 1, 2 would be there, Y prime. And 1, -1.5, that's Z prime. So if I join it together, what I should get is a similar rectangle. And the similar rectangle is 1/4 the size of the original. All right, it's 4 times shorter this direction, and it's 4 times shorter this direction. And if we just want to double check, like we said, we can always take our ruler, line up Y and Y prime, and that should be in a direct line with the origin. So all these do that. X and X prime, W and W prime, Z and Z prime. And we'd see how everything just kind of shrunk along those lines until we got 1/4 the size of the original. Okay, so that's how you reduce or enlarge with respect to the origin. Now, like I mentioned before in I think it was the reflections unit, that this is just the beginnings, that we are always going to be enlarging or reducing things with respect to the origin, but just realize later that there will be some problems where it isn't with respect to the origin. For example, let's say I wanted to take this problem here and dilate it by a scale factor of 2, okay, which is no different from before, and there's my image. But in this time, I am not going to do it with respect to the origin. I'm going to do it with respect to this point, okay? So again, just realize that you are going to take this further. You're not going to have to do this, but the idea is still the same, that what I want to do is I want to take my dilation point, I'm going to take these coordinates, and then mathematically I'm going to figure out, well, if this is a distance of 1, I want to go twice as far. I'm going to go out a distance of 2, and that's where that point would end up. This is very similar to our rubber band activity, and I just wanted you to see this because not everything is always with respect to the origin. All right, so there's this one here. Here I'd go out this distance to here. So here I want to go twice as far to here. And then if I line up here, these two, I want to go this distance twice as far, which would put that point here. And here's my dilation of 2. I get a similar triangle, but it's twice as big. Okay, so this is kind of just a preview where you'll see this taking place later on, where that point of dilation doesn't always have to be at the origin, but for our beginning problems, that's where we're going to start off.